Hi there, my name is Daniel Bidemi Bisanya, and I'm a physics graduate from the University of Ibadan, and I'm a data analyst. I have a strong analytical mind. I can actually analyze data, different sorts. I can clean data. I can bring out meaningful insights from data. And apart from that, I'm also a very, very experienced teacher. I've been teaching for well over 7 years. I've taught mathematics, physics, computer science, basic science, to different cadres of students. In fact, I have taught across all the institutional cadres. That is, from primary school to junior secondary school to senior secondary school. I have taught across all the classes. And so I actually know how to deal with each cadre or each level of students. So this actually has helped me to know how to relate with students based on their levels. And also, I'm a very, very lover of knowledge. I'm a good lover of knowledge. I love to acquire knowledge, to know more, and then to also impart knowledge to people. Because it makes me happy when I see people do well in their fields of endeavor. So today, I'll be giving a demo class on basically I'll be teaching physics. And what I want to talk about, as I've uploaded on the site, is electricity. So my screen is on displayed on the board. So I'm talking about electricity. Basically, I want to talk about resistors and electric circuits. So, but basically, I won't spend much time on electric circuits. The major focus of this demo class is just resistors, just to show how we can arrange and calculate resistors basically. But before we go ahead to the calculations, I'm going to talk about the definition. What is a resistor? That is, what is a resistor? Okay, so to answer that simple question, I'll just quickly state what a resistor is. A resistor is an electrical component that offers opposition to the flow of electrical current. So that means in an electrical circuit, we can have a resistor, right? A component that offers opposition to the flow of current in the. So now, they are given that normally if you have a wire, let's say this is a wire AB, and I apply a potential difference across its ends. The potential difference is measured in volts, right? So it's the same thing as you applying voltage actually across the ends of the wire. What happens is that, okay, let's say this is the region of high potential and this is the region of lower potential. So what will happen is that electric current or electrons will flow in this direction, isn't it? So now, looking at this now, every material, as it were, has this inbuilt resistance to the flow of electrical current. You get that? And that, so resistance is actually the opposition that is offered to the flow of electrical current by an electrical conductor. You get that? So now, let's say this is an electrical conductor, alright? So it has an internal resistance that is offered to the flow of electrical current. So now, once there is potential difference across the ends of this wire, electrical current is bound to flow. But then there's also a factor which is resistance that is in place and that is resisting the flow of the electrical current. Look at it. Let me quickly. There's a way I can make this more practical. Okay, let's say you have a pipe now. For instance, look at this. This pipe is big, alright. But look at this one. I want to draw a thinner pipe. See that this one is thinner actually. So now you are doing that if I should pour water, alright, into this pipe, and I pour water into this pipe. When you are doing that, the flow of water here will be easier rather, compared to the flow of water here. The water would rush more here, alright, and it will be easier for it to pass through this pipe than through this pipe. So that means the smaller the pipe, alright, the higher the resistance. So now, when you talk about the smaller the pipe, that is talking about the thickness of the pipe now. So that means we can actually look at it from the point of area, alright? So the cross-sectional area. So that means the smaller the cross-sectional area of this pipe, alright, then that means what? The more the resistance. Okay, so that means we can actually bring that into electricity. So the thinner the wire, the more the electrical resistance. The bigger or the thicker the wire, the lower the electrical resistance. It's just the same thing as you apply in the pipe. So now, when water is flowing through this pipe, don't forget there are two things that are in place. Potential difference, because obviously water is coming from this end. So this end has higher potential compared to this place which has a lower potential. So water will flow from higher potential to lower potential. Alright? And so, let's say let's say this pipe is not a plastic pipe, let's say it's a rubber pipe. Then I attach a rope now, like this, and then I tighten this rope. If you know what will happen, let me just make it more picturesque. This is what will happen. The pipe becomes something like this. Sorry, okay, let me clean that. That looks like an error. Okay, it's not passing across here. Let me clean this. Okay, so I'll draw it again. So look at that. So this is it. Exactly, this is what I want to do. So now, this is the wire that I'm using, to the rope I'm using to tighten. So this thing is now I've tightened it in this place. So if I should pour water in this pipe, at first the water would rush, but when it gets to this place that is narrow, the water will require more thrust or more force for it to pass through to the other side of the pipe. So that means I can actually look at these ropes that I have tightened here as a resistor. Okay, as a resistor that it is providing opposition to the flow of water through this pipe. So you can look at the resistor as this rope that tightens the path of the electrical current. So now, so far we've been talking about three different things. We're talking about the resistor, okay, resistor R, okay, or resistance, okay. We're talking about the voltage. We're talking about voltage V, and then we're talking about current so far. These three things, current I, so far. So now, there's a law in physics that connects these three factors, or these three entities together. Okay? And that is called the Ohm's law. I'll spell that. Ohm's law. Ohm's, the apostrophe is there. Let me just. Ohm's law. Yeah, so the Ohm's law, what does it state? Before I say the Ohm's law, I'd like us to know that the resistance of a resistor is measured in ohms. And the symbol is this omega. Okay? Voltage or potential difference, alright, is measured in volts. And the symbol is just this V. And current, alright, is measured in amperes. And the symbol is this A. Okay, so we'll be using these symbols a whole lot. So the current itself can be represented as I, resistance R, voltage V. Do you get that now? Okay, so now, I believe you get that. So now, Ohm's law. So what does Ohm's law really state? We're looking at conducting wire, current, and voltage. Ohm's law brings the relationship between the three together into one. So now, what Ohm's law states is that, look at that, let's say you have a conducting wire, okay? It states that the current that is flowing through this conducting wire, this is high voltage, low voltage, right? So, it says that the current along a metallic conductor. Now, you should know that Ohm's law is applicable to metallic conductors, alright? So, the current that is flowing across or along a metallic conductor is directly proportional to the potential difference across its ends. Don't forget this potential difference, alright? Okay, higher potential, lower potential, and then current is flowing. So this is what Ohm's law states. It states that the current that is flowing through a metallic conductor is directly proportional to the potential difference across its ends, given that resistance and every other physical conditions are kept constant. Temperature is also part of the physical conditions. So You know that every other thing is kept constant, alright? Then we have that I is directly proportional to D. So now, looking at it, Ohm's law says that given that resistance and every other physical conditions are kept constant. So that means looking at, I can mathematically I will express this as I equals to KV, isn't it? Alright. So now, but by experiment, we found out that this K here, this constant is actually 1 over R. That's 1 over resistance, or you can also call that conductance anyways. But then 1 over resistance. So I will switch this K for 1 over R. So I'll have that I equals to then 1 over R, right, times V. Then this implies that I will be equals to V over R. Okay, so if I should cross multiply, I have that V equals to I R. So this is the mathematical representation of Ohm's law. Don't forget that V is measured in volts, alright, volts. I is measured in amperes, okay, and R is measured in ohms. Okay, so very good. So this is the simple representation of the Ohm's law, and this law is very, very useful when it comes to both current and static electricity. So current electricity is very, very useful. So now we'll be moving ahead. I just want us to take some examples on Ohm's law. Alright, so I'll give, because I have my lesson plan drafted here, so I'll just read the equation out, then we'll solve it together. Okay, look at that. They say if a bulb draws 2 amperes of current, so the bulb draws 2 amperes of current. So that means current I equals to 2 amperes, okay? And it said when connected to a 12 volt battery, so that means the voltage is 12 volts, okay? Then I said find its resistance. So we are looking for the resistance, okay? Quite simple. You just have to say that V equals to I R, basically. Alright, so my V is 12 equals to what is my I? 2 times R. And I can make R the subject of formula and I have that R equals to 12 over 2, and that is what? 6 ohms. As simple as that. So, that's the way you deal with Ohm's law. You can also, they can give you resistance and current to find voltage. They can give you voltage and resistance to find current. You can always just maneuver your way around and then always solve problems that are related to Ohm's law. Now, that's said about Ohm's law now. So now, imagine an electrical circuit. For instance, so let's say you have battery or a cell, pardon me, and then you have a resistor. You must have seen things like this before as a physics student. You have a resistor, and you are, let's say, what should I put there? Let's say a bulb, for instance. You have a bulb here. So, and it's all connected together. The current would flow, alright, and then pass through and then comes to this bulb and then it gives light. You can also have a key. Let me try to put a key. Okay, I'll just put this. Okay, let's say this is a closed circuit now. So this is a key here. So now or a switch, I know what you call it. So this current flows and then when this, because this is a closed circuit, this bulb gives light. Okay. So now, let's say this is R1 and R2. We want to look at how do these resistors affect this circuit. So we must actually know how to manipulate or deal with resistors and circuits. And hence that will lead us to the arrangement of resistors. So arrangement of resistors, So we need to know how resistors are arranged first before we can calculate or account for resistors in an electrical circuit. So now, there are 2 types of arrangement. We have the series arrangement, okay, and we have the parallel arrangement. Okay, so I'll do it in a tabular form. So now, series arrangement is just something like this. I'll explain. Okay, so you have this, okay. You have this. So I forgot to mention something earlier on. I'll mention that now. Resistor, alright, let me create a space up of this. Okay, let me do beside this space. There are two symbols for resistor. The symbols for resistor. There are two symbols. Is that you have this, okay, or you have this. These are the two symbols for resistors. Okay, so it's different from, don't mistake this for an inductor. An inductor looks like this. Alright. Okay, so this is an inductor. It is different from a resistor. You see, this is like a coil, right? But this one is just like zigzag kind of. So this is a resistor. Okay. Okay, so this is a resistor. Resistor. Alright. While this is an inductor. Okay, so these are the two symbols used to represent a resistor. Well, we have something called the rheostat, which is a variable resistor, but then that's not too much, it's the same thing. Once I just put an arrow here like this, on this or on this, on any of the two, on the two symbols, once there's an arrow like this, then it's a rheostat, that is a variable resistor. But here we are not dealing with the rheostat, we are just talking about the resistors generally. So now, let's go ahead now. So now, you have this, so you can see me use this box-like arrangement for resistor, and you can see me use that zigzag kind of representation for resistor. Any of the two is acceptable. So now, this is a series arrangement of resistors. Okay, look at this. I will show you a parallel arrangement of resistors. Okay, this is a parallel arrangement of resistors. So now, I'll quickly explain to you how to identify series and parallel arrangements, because it can actually be somehow confusing. Say they give you something like this now, for instance, let me draw this very common confusing circuit on the board. Students usually don't get this most of the time. And so let's say you have something like this, okay, and then you ask if this is in series or in parallel, or to calculate the total sum. Okay, let's say you have the wire coming from here, okay, the circuit coming from here, okay, so starting from here, and then let's say it ends here, kind of. Okay, so this is the beginning, the source, okay, and then where it terminates. So now, so you say if you calculate the total, what's it called now? Total resistance, yeah. Students usually can just get this list up. You look at it, oh, is it in parallel, is it in series? Now I'm going to show you the easy way. It's just like a trick. How you're going to know if something is in parallel, if the resistors are in parallel or they're in series. So let me clean this. I drew. So now I want to show you how to easily identify when resistors are in parallel or in series. So now I'm going to be using the stickman illustration. So look at this now. I called it the stickman illustration because I feel like that's the best way to explain it. So imagine this is, what is actually moving through all these components, circuit, is electrical current. Don't forget. Once there's potential difference, current moves. So now, imagine this stickman is the electrical current that is trying to move across all these resistors coming to this end. Alright, this is the starting point, this is the source, and this is the end. So now we are going that this guy just simply walks all through, alright, gets here, walks all through, gets here, walks all through, and then comes here at the end of the day. Nothing happens to the guy is fine, okay? But now look at this. In this parallel arrangement, look at this guy here. This guy gets to this junction here now. And this guy really wants to walk through these three resistors at the same time. How can this guy do it? This guy cannot possibly, walk here, and walk here at the same time. So something has to happen. Okay, so This guy has to divide itself into 3. See, let's say just the head of the stick man goes here, then the arm of the stick man goes there, and then the leg of the stick man goes there. So it walks through after this becomes current 1, alright, current 2, and current 3. You know, this current 1, current 2, current 3, this is the original current, right? They all sum up to give us this original current I. So if I say that I is I1 plus I2 plus I3, because it is this stick man that divided itself into this 3. So it cannot pass through these 3 resistors at the same time and then come back at this node. In this node where it divides itself, comes back at this node and join back together again and then comfortably walks to the end. So whenever you have this type of illustration happening, then the current has to divide itself either into 2 or 3 or 4 or 5 or 6 or 7, as many as possible places. Then that is a parallel arrangement. But when the current has to move through without any division, then that is a series arrangement. So now, let us go back to that box that I drew earlier on, and let us see if we'll be able to figure out if it is a parallel arrangement or a series arrangement. So look at that. Oh my, I don't like the way this is going. It's going up. Okay. I need my hand to be straight. Alright guys, this is good. So look at that, you have, let me draw this, and you have this. Okay, so you have box 1, resistor 1, resistor 2. Okay, here you have resistor 3. Okay, let's say this guy goes this way, and then here you have resistor 4. Okay, let's say that's all. So node 1 and node 2. Okay, now, so this is R1, R2. We call this R3, and then this is R4. Now, looking at this, so let us look at it. Is this really in parallel or in series, or both parallel and series? Well, let's look at it. So now, look at this stick man here, or the current. Okay, I'll use the stick man as an illustration. Upon getting to this node, you are doing that the stick man has to divide itself into 2. Okay, so the upper part of the body comes here, alright, and the lower part of the body comes here. Okay, so we now have the current I1, so let's call this I1, and then you have the current I2, because this is the current I. So we have that I equals to I1 plus I2 at this junction. So you see that I1 would walk through R1 and R2. Okay, in fact, if you get to this junction, it will just simply come this way, it's not dividing, and still walk through R3. Do you get that now? So this I1 would comfortably walk through R1, R2, R3 and get to this node and stop. Okay. Sorry, just the R. Now look at this I2 would only walk through R4, alright, and get to this node and join together with this guy. Okay? And then you have the complete stickman. So what does that suggest to you? Now, this guy divides at this junction. Okay, so that means everything from this junction up and everything from this junction down will be treated separately or differently. But now, from here down to this R3, from this R1 down to this R3, the current that is passing through, which is I1, is not divided. So what does that suggest to you? From R1 down to R3, they are all in series. So we have R1, R2, R2, and R3 in series, okay? And also, we have R4 standing on its own, okay? Then, looking at that, R1, R2, R3 in series, R4 in series. So now, but the current is divided at this junction. So this means that this whole combination is in parallel, okay, with just this guy. So now, how do I combine resistors together? Let us go back to that diagram of series and parallel. So now, let's call this my R1, R2, R3. So, combination told us that R total, okay, will be equal to R1 plus R2 plus R3 plus we have till infinity plus Rn. This is sum of resistors in series. Alright, so now in parallel, what we are told is that R total, okay, is now this is, let's see this as R1, R2, R3. So R total is 1 over. So now look at that. This place is too small. You know, I'll just create another space down here. Okay, let me use this place to explain that. So we have that. Let me say 1 over R total so that it won't confuse you. 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3 plus plus 1 over Rn. Okay? So, to get the R total now, R total simply will be 1 over R1 plus 1 over R2 plus 1 over R3 plus ellipsis plus 1 over Rn. Then I'll close my bracket and I'll add inverse. Sorry, this is going up. Then I'll add, give me a moment. Okay, I don't like where my tab is going. Okay, so then this will be inverse. Because you know this is inverse here, so I have to inverse everything to get my R total. So this is what you're going to have 1 over Rn here. Okay, so that is that. So now, let me just quickly come back to this one that I explained here. So now, because we have established that R1, R2, R3 are in series, so that means I can total the resistors through which I1 passes through. I1 will pass through 3 resistors, R1 plus R2 plus R3. Let's call that R small letter c. Okay, the total for the series. Then you know that I2 we also pass through R4, isn't it? Well, we have that this R total, okay, is I1, R4 is I2, so that means they are in parallel, isn't it? So to total it together, I will now total RC and R4. Do you get that? So the total resistance altogether will be 1 over RC plus 1 over R4, then I'll bracket it and then I'll inverse it. That is the way you get the R total for that combination. So let us give a picturesque example. Like we are going to be dealing with figures now instead of R1, R2. This R1, R2 can be somehow confusing. So now I'll just give. Okay, so look at that now. Let's say you have these and then you have a resistor. Let's say this is 2 ohms here. Okay, you have these, you have these, you have these, and then I'll quickly make this quick because of my time. So yeah, this is, let's say this is also 2 ohms and then this is also 2 ohms. So I want to get the total resistance here. So all I just need to do is I need to have my current, alright, passing through this place. The current is still the same current here, right? But upon getting to this node, divide to I1 and I2, isn't it? So that means at this junction, these 2 resistors are in what? They are in parallel. Okay? Okay, let's say this is R1, this is R2, this is R3. That means R2 and R3 are in parallel because the current is dividing at this junction. So I'll start from here. Okay? So I need to like parallel 2 of them and make it into one, form it together. So what I'll do is that I'll say that I'll use a small letter T for that because that's not the total resistance. It's just the resistance for the parallel section. So I'll say that R2 will be equal to 1 over 2 plus 1 over 2, alright, inverse. Okay? So this will be, what is 1 over 2 plus 1 over 2? There's obviously 1 inverse, which is 1 ohm. Okay, so that means these 2 I have paralleled them and then made them into one. So this diagram now looks like this. Look at that. Okay, this is 2 ohms here, and then this now becomes 1 ohm. Alright, and then of course I've paralleled them together. So the current now flows through the 2 at the same time. Alright, so without division. So that will suggest to us that the R total that I calculate, which is 1 ohm, is in series with these 2 ohms. So that means the R total now, okay, the total now will be 2 ohms plus 1 ohm. Alright, and that will be what? 3 ohms. Hope you get that now. So that is basically how to deal with resistors and how to calculate resistors in circuits. So I'll see you again next class. Same time, same day. Thank you very much for the time. Bye. Any question you have, let me know in the comment section if there's anything like that. Alright, bye.